Chapter 10, Section 3, Multiplying Radical Expressions. Well, in this lesson we're going to talk about multiplying radical expressions, simplifying by factoring, and multiplying and simplifying. And what they're going to really go through, when we talked about in the prior lesson that these radical symbols or these radical expressions, we found a way to write those as exponents, and they're really just going to be applying the exponent rules that we've had before and do that. Though it's good to go through this because we're going to look at a couple of different ways to simplify these, and they're going to create some new rules about how they want the answers to be. Just like when we have fractions, um, we always want the fractions in simplest form, which simplest form means that the only common factor between the numerator and denominator is 1. So um, we're going to look at these things. These rational exponents can be used to derive this rule. And I guess I just kind of skipped over that without talking about that. But here is the product rule for radicals. And like I said, it really is the same as if this was square root. We could say a to the 1/2 power times b to the 1/2 power is the same as a times b to the 1/2 power. And basically that's the same thing. Here we have an index number here of 3, so that's a cube root or the 1/3 power and so on. But like I said, they're going to give us the rules with the radicals, and we're going to go through some strategy really using that rule. And they have some cautions here right away. The product rule for radicals applies only when the radicals have the same index. Or in other words, if we were talking again about exponents, it would be the same exponent and so on. But that's a common error. If they mix the radicals with different indexes, we're probably not very familiar with seeing that very often. We have to be careful not to make this mistake right here. The other caution here too is that when you get the square root of x squared minus 9, we can't break that out and to do that. That only works with multiplication, and later on we'll talk about division too. So using this rule, like example A here, I have the square root of 2 times the square root of 7. Well, I can rewrite that as a square root of 2 times 7, or the square root of 14. Here they have a little more complex expressions here. The square root of x plus 3 times the square root of x minus 3 would be the same as writing it as the square root of those two things multiplied, and that's difference of squares. So we could just put it as the square root of x squared minus 9. And they note this, the product of two square roots is the square root of the product. That's basically the rule that we went through. And this works with fourth roots here and so on, and with fractions, that this is just a multiplication, and we can end up with some things here. Well, now here comes that word factoring again, and factoring again is that we're going to break it down into multiplication. The parts of the multiplication are factors. So let's read through this part here. It says the number p is a perfect square if there exists a rational number q for which q squared equals p. We say that p is a perfect cube if there is some number q that could be cubed that equals p, and so on. They're talking about these perfect nth powers is what they're getting to, and why those are important. That we want to take out any perfect squares, because if we don't have a perfect square or perfect cube or perfect nth power, we end up with an irrational number, which is the only thing we can do on a calculator is give an approximation of that. But we want to simplify a lot of things and leave it at the very minimum like a square root of some prime numbers multiplied together, and so on. But using this product rule, the same rule we went through on the other page, we can go the other way, right? We can say if I have the nth root of a times b, I could break that into the nth root of a times the nth root of b. And then it says a and b have to be real numbers. So if we have something like the square root of 20, we could break 20 into factors. Now it isn't prime factored, but we'll talk about that a little bit later. But they say, well, let's say that 20 can be represented by 4 times 5. So we could say square root of 20 is the same as the square root of 4 times 5. And then using this product rule, we can say, well, that's the square root of 4 times the square root of 5. Well, the reason they pulled out this factor of 4, that's a perfect square, is that we can get the exact value for the square root of 4, which is 2. So we end up with 2 times the square root of 5. Now, square root of 5 is not a perfect square. We can only give approximations for that square root of 5. And it's kind of like the principle of when we talk about pi, when we're talking about circles and stuff like that. Pi is an irrational number. They leave that as a symbol because depending on the amount of accuracy you need when you're doing an application of this, or you have an application or a word problem, there's a big difference between whether we're talking about flying objects through space or we're talking about just shooting maybe a marble with a slingshot and we're trying to get trajectory or something like that. We probably would make a difference on how accurate I may make this square root of 5. So we leave it that way, hopefully, and then at the point of the problem where we're saying, now how accurate does this need to be, then you can apply that and you can bring out a big scientific calculator and take square root of 5 out, maybe even 20, 30 places past the decimal place, if you need to, right? Well, here's a strategy, right? To simplify a radical expression with the index n, we have nth root, would be another way to say that, by factoring. If possible, express the radicand, the part underneath the radical symbol, as a product for which one or more of the factors are perfect nth powers. If it was square root, we call it perfect square, perfect cube, and so on. Rewrite the expression with the nth root of each factor. Simplify any expressions containing perfect nth root powers. That's just like taking the square root of 4. Simplification is complete when no radicand has a factor that is a perfect nth power. So in other words, I'd look at this 5 and I say, well, there's no factors of 5 that could be perfect squares except 1, really, right? And 1, when we're talking about multiplication, isn't necessary to write out. So simplify that by we making sure that there's no perfect square factors still under the radicand, okay? Or in the radicand, excuse me, under the radical symbol. It is often safe to assume that a radicand does not represent a negative number raised to an even power. We will henceforth make this assumption unless functions are involved and discontinue the use of absolute value notation when taking even roots. In other words, they're just trying to reduce the amount of steps that could be possible. So they're going to kind of go back to that implied root, and we're going to disregard that. But there are some times where they'll probably remind us you got to make sure, especially in functions, that we're representing all possible solutions. So they're simplifying some stuff here. So I got the square root of 200. Well, I want to find perfect squares because it is square root. They say, well, 100 is a perfect square. That's 10 times 10. And we rewrite this as the square root of 100 times 2. Well, then we can break that as square root of 100 times square root of 2, which is 10 square roots of 2. And they show this here. We have 25 as a perfect square, x squared is a perfect square, and we still have then 2 times y. So we separate those in a specific way to say, hey, 25x squared is a perfect square. I can take the square root of that to be 5x, and then that's times 2y. Here we got a cube root issue. I need to recognize that 8 is a perfect cube, or negative 8 is in this case. So I'd say negative 8 times 9 is a way to express negative 72. I take the cube root of a negative 8 and get negative 2, and the cube root of 9 is still there. This would be a very tempting area here. Hey, 9 is a perfect square, but we're not looking for squares. It's a cube root. So be careful there. They do some more here. You know, there's a trick to finding these perfect squares. If you're good at that, and I recommend this, it would be good to practice thinking about what perfect squares are. We run into that a lot. It's going to save you some time. You know, it's 1 squared is 1, 2 squared is 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144 is 12 squared. And I think if you can get a pretty good handle on those numbers, you know, you're going to be looking for those when you're factoring, could save some time. Now, there's another way to look at these factors here. Now, perfect fourth powers, I don't think I can name those very well. You know, 1 is 1, and then 2 to the 4th power is 16, right? And so on. It would, if you're really good at numbers, maybe you could do that. But well, they do find these perfect fourth roots, right? And put those together, and then they end up with 3x, because 3 to the 4th power is 81. X to the 4th power, you know, is x to the 4th power, right? So we do the root and take it times what's left, and we end up with that. Well, they're going to show us something here which is very important, because like I said, if I'm looking for perfect fourth to the 4th power stuff, like I said, that's not so easy to see in numbers. Well, why don't we prime factor everything? If we prime factor 162, we end up with this 3 times 3 times 3 times 3 times 2 times all these x's. And you could write this as 3 to the 4th power, 2 to the 1 power, and x to the 6th power. But they separate that and say, well, we're looking for perfect 4th power stuff, right? Well, notice when we break this out in prime factoring, I take my groups of 4, right? This would be 3 to the 4th power, x to the 4th power. Well, when I take the root of those things, I get 3 and x, and then I still have the 4th root of 2x and x right here. To me, this would be a lot faster way to find these things rather than trying to figure out what 3 to the 4th power is and recognize that I can take 81 factor out of 162. This is very important, be very useful. In fact, usually when I run into this stuff, I always go to prime factorization. It's a way to make sure I don't miss any factors that could be perfect, or things that I can take the root of, basically, and get exact values. Example 3, now we have a function. And like that note said at the beginning of this section here at these examples, that if we do not have a function, let's just forget the absolute value thing for even roots. Well, here it comes back, because we do have a function. f of x equals the square root of 3x squared minus 3x plus 3. And find the simplified form for f of x, because we're working with a function. Assume that x can be any real number. Well, they begin by factoring again, right? Just like we're up here, we start factoring some stuff. Well, there's a common factor of 3. Don't forget that. Boy, that it gets very complex doing a lot of these to find perfect binomial squared and so on if you don't see that common factor first. And that's what they do here, 3 times the quantity x squared minus 2x plus 1. Well, this is a perfect square. This is something squared and this is something squared. I'd end up with x and 1. If I take those times each other and double it, I get 2x. And here they got a negative 2x, so it's got to be x minus 1 to the 2 power. Hey, that's a perfect square, right? So I can take the square root of this and times the square root of this, and I end up with the absolute value now of x minus 1 times the square root of 3. Now, these type I think are pretty easy, really, because if I really am comfortable with my exponent rules, and later on we're going to show us some things that I would prefer to really, to me, especially when we get into these types, I could take the square root symbol right here and I can make that be a exponent, can I? So I could do some stuff here that we'll go through in the lessons, and they are kind of converting this in the middle of this work, where I would do it right away, but they break out the even exponented things. Even though we have x to the 7th, well, I can represent x to the 7th as x to the 6th times x to the 1. Y to the 11th can be y to the 10th times, well, notice these exponents are even because really I'm going to take half of that will be the root, because this square root is really the exponent of 1/2. So we have a power of a power situation. So the square root of x to the 6th is like taking 1/2 times 6, and you end up with x to the 6 over 2, or x to the 3rd. 1/2 of 10 is 5. 1/2 of 8, this exponent is 4. Kind of skipping this fractional exponent. They just simplify those fractions. And then what's left? I still have this x, y, and z, so I still have all this times the square root of x, y, and z. We can check that a lot of different ways. So they're kind of going into this again here, this cube root. I want things to be, the exponents to be multiples of 3. So I could have a to the 3rd and a to the 6th, a to the 9th, a to the 12th, and so on. So I'm looking for multiples of 3. They pulled out this 8, which is really 2 cubed, 2 to the 2 power. See, I would factor this all out, not look for perfect cubes. I'd say this is 2 to the 4th power, which I could separate to be 2 to the 3rd power, which is 8 times 2. Just like I'm doing with these exponents. And then take the cube roots of the ones that we separated out with reason, because we get perfect cubes, right? And then they show this again to what I was talking about. That this, to me, this is a preferred method. This always works. And it also, by doing things in this way, I don't think I would write it all out. I would think about perfect cubes as being any exponent that is a multiple of 3, right? So I could recognize that a to the 6th is a perfect cube, instead of saying I got to have a group of 3, 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 and so on. I know that this is 12 of them, right? I can take 1/3 times 12 and I get 4, right? So they give us this one with 5,000. So I would definitely just prime factor 5,000. This one works. X to the 12th is a perfect cube because 12 is a multiple of 3. If I take 1/3 of 12, I get x to the 4th, right? And so on. 1/3 x to the 12th, the 1/3 power, right? Powers you multiply. Well, y to the 13 is not, but I can write y to the 13 as y to the 12 times y. And z to the second, I can't do anything to that. I need at least a multiple of 3, but it's not there. And 5,000 is, 50 times 100, and then I'd break that down into prime factors to figure out what numbers I'm going to end up with. Well, we're talking about fractions and simplifying stuff like that, and here we come with multiplying. Just like when we're multiplying fractions, we're going to find some opportunities to pre-simplify, is to put things together in a way that's going to help me simplify my solution, or not necessarily a solution, but a simplified radical. So they say, look at this example, square root of 15 times square root of 6. We could write that as square root of 15 times 6, right? Which is 90, and then they separate 9 times 10. Well, I could also prime factor this. 15 is 3 times 5, 6 is 2 times 3. So I'm going to end up with 3 squared times 2 times 5, or this square root of 9. I think that's a much, much easier way to go, rather than saying, hey, I want to build a number, then pull out perfect squares and so on. Prime factor it. We could write this as all in prime factors. Look for your exponents that are going to work with this root. Will save you a lot of times and probably a lot of steps, which can save you a lot of errors. So they're doing this with the perfect ones again, but then here at the end of this thing, hey, you could prime factor this whole thing, and there might be some opportunities to make this simpler, especially when you get into this complex stuff. But I would even do it up here, like in this A one. Why worry about having, well, I got to make sure I pull out my perfect squares. Well, if I prime factor, I'm going to see those a lot more easily. And that's lesson section 3.